Right, so the topic of my lecture for this week is going to be neutrino physics. And this will then be complemented by the lecture by Yvonne Wong, which I'm sure will also have a large neutrino component. So her lecture will be on cosmology, where neutrinos play a very important role. So. And the plan for this first lecture is that we are going to talk about how neutrinos fit into the standard model and how neutrinos may get their very small but non-zero masses. And then in the subsequent lectures we are talking about neutrino oscillations. We are going to talk about neutrino oscillations at great length. We are going to talk a little bit about neutrino-nucleus interactions, about new physics in the neutrino sector. Yeah, but for today it's going to be a lot about neutrino masses. So to get started, let's look at how neutrinos fit into the standard model. So we start with a piece of the standard model Lagrangian, namely the terms relevant for neutrino physics. And the very first thing we need to start with is a sum over flavors, because as you know, there are three different types of neutrinos: electron neutrino, muon neutrino, and tau neutrino. So whatever we are going to do, we need to do it to all three of them in the Lagrangian. So there is the neutrino kinetic term. There is going to be the neutrino interactions, and since neutrinos interact only weakly, not electromagnetically and strongly, that means there's only going to be couplings to the W boson and to the Z boson. The coupling to the W comes with the weak coupling constant G divided by square root 2. The W field, in this case W mu plus, nu alpha L bar gamma mu E alpha L plus the Hermitian conjugate vertex. The coupling to the Z comes with a coupling constant G divided by 2 times cosine of the Weinberg angle. Right, we are after electroweak symmetry breaking, so I've already separated the photon from the Z, and the Z is the mixture of the neutral gauge bosons that comes with 1 over cosine of the Weinberg angle. There's a Z mu, nu alpha L bar, gamma mu, nu alpha L. And then there's going to be a mass term about which we are going to talk about in a bit. So the crucial pieces here are, I already said, there is a flavor index because neutrinos exist in presumably 3 different flavors, maybe more, but definitely not less than 3. What you may also notice that I've put on all the neutrino fields, I've put a little L here, which is the left-handed projection. So that means if I write the neutrino as a Dirac field, then this little L means that it's projected with the 1 minus gamma 5 over 2 projector. That's a reflection of the fact that in the standard model, in its original formulation, only left-handed neutrinos were needed. Right-handed neutrinos only come in when we write down neutrino masses, but at the time there was no evidence for neutrino masses. So if there's no evidence, there's no need to introduce neutrino masses, and without neutrino masses, there's no need for introducing right-handed neutrinos. Now there's, of course, always a debate whether we should call neutrino masses physics beyond the standard model or not. But in the end, that's more or less a philosophical question. My take on it is we should no longer call it physics beyond the standard model, because if we take the discovery of neutrino oscillations in around 1998 to 2002 as the point where neutrino masses were established, then by now the standard model with neutrino masses has existed for longer than the standard model without neutrino masses. Right, and I think the rest of the notation should be pretty obvious: the W and the Z boson fields, and here the charged lepton fields. And of course, in terms of Feynman diagrams, the vertices I've drawn here are, as usual, the W coupling to a neutrino and an electron, and the Z coupling to the neutrino. Okay. But now, as I mentioned, we have evidence that neutrinos have masses. We are going to talk much more about tomorrow why we have evidence that neutrinos have masses. But the fact is, we need to introduce neutrino masses. So let's first talk about neutrino masses, therefore. And the first type of neutrino mass term that I'd like to talk about is a Dirac mass term, because that's the ones that we are most familiar with. So the simplest possibility is that neutrinos get their mass in exactly the same way as the other fermions in the Standard Model do, namely by coupling to the Higgs. So the idea is that we write down a mass term of the form sum over alpha and beta. These are again flavor indices. Some coefficients which we call m alpha beta, nu L alpha bar, nu R beta, plus Hermitian conjugate. So what have I done here? Well, first I've introduced right-handed neutrino fields. Right? That's what a Dirac mass term, the one that you're familiar with from QFT 101, that's what it looks like when you decompose it into its left and right-handed components. So if you have, let me write that again in a different color. If you have a Dirac spin or psi, then you can decompose it into, in the Weil representation, you can decompose it into the left-handed component and the right-handed component, and then a mass term of the form m psi bar psi turns into m psi bar left psi right plus m psi bar right psi left. And here I'm always working in this chiral notation, so I've immediately done this separation into left and right-handed states, because in a sense they are independent degrees of freedom, the left and right-handed states. Okay. Now, the deeper origin of such a mass term could, of course, be the Higgs mechanism. So above the electroweak scale, we would have a Lagrangian that contains a term of the form sum over alpha beta times a Yukawa coupling alpha beta times the left-handed doublet bar alpha times the Higgs field times the right-handed neutrino. So these here are the SU2 lepton doublets. With the usual convention that the neutrinos are in the upper component and the charged leptons are in the lower component. That's the convention I'm using here. That's the convention that most of the textbooks are using. But as you know, in principle, you can also do it the opposite way, because it's just a matter of an SU2 rotation. So L here is neutrino left, charged lepton left. Here the Higgs doublet. This is I times sigma 2 times the Higgs doublet with the coefficient I sigma 2 essentially flipping the lower and upper components of the Higgs doublet while maintaining SU2 invariance, so while keeping the SU2 transformation properties of the field still those of an SU2 doublet. And there needs to be a star here. So that term now looks exactly the same as a mass term for the up-type quarks. Okay, and then as usual, when the Higgs acquires its vacuum expectation value, that vacuum expectation value times the Yukawa coupling turns into the mass, and the neutrino field from the L doublet and the right-handed neutrino field end up here in the low-energy Lagrangian. Now, in principle, With this, we can declare success because that is a way of explaining neutrino masses and explaining all the experimental evidence we have for them. Theoretically, one can argue about how nice it is because, as we know, neutrino masses are extremely tiny, which means that these Yukawa couplings would need to be extremely tiny. So, to explain the observed smallness of neutrino masses, the Y alpha beta need to be tiny. And by tiny, I mean 6 orders of magnitude smaller than the Yukawa coupling of the electron, which is the smallest among the Yukawa couplings known in the standard model. So there's nothing in principle wrong with that, but of course it would be nice to have an explanation. And before we go into how we could potentially explain the smallest of these masses, I would like to make one more comment about the relation between the introduction of right-handed neutrinos and the emergence of neutrino masses. Because what I've effectively done is I've introduced 2 new degrees of freedom into the theory. Before, over here, there were only the left-handed neutrinos and their antiparticles, so that's 2 degrees of freedom. Now, I have right-handed neutrinos plus their antiparticles on top, so I've had to introduce 2 extra degrees of freedom into my theory. And the reason this is necessary, one way of understanding this is the following. Think about a particle with left-handed helicity. So we imagine we have a particle here that's propagating in some direction with a momentum p, and its spin vector is anti-aligned with the momentum vector. So that here we call S the spin. Now, if the neutrinos are exactly massless, this movement is happening at the speed of light. But if they are massive, it has to be below the speed of light. And that means I can, in principle, boost my coordinate system to a frame which is moving faster than the neutrino. For massless neutrinos, I can't do that, but for massive neutrinos, I can always do that. So here we apply a large boost. So we could now end up in a reference frame where the neutrino is moving in the opposite direction with some momentum p prime. The spin is unaffected by the boost, so the spin is still oriented here towards the left. So this means through this large boost, we've turned a left helicity state into a right helicity state. This is not possible for massless particles, but it is possible for massive particles. And that's the reason why extra degrees of freedom arise when a particle is massive. So large boost can turn left helicity state into right helicity state. If and only if the particle is massive. Okay. So far, so good. So this was all a formalism that we're all very familiar with from the standard model. But now for neutrinos, it turns out there's another possibility to introduce masses, and this is a Majorana mass term. So let's talk about those. The basic idea is that, as we've seen and explained, a mass term is always a term that couples a left-handed state to a right-handed state. Now, what I call nu left here is a field that has 2 degrees of freedom, the left-handed neutrino and its antiparticle. But the antiparticle of a left-handed state is a right-handed state. So the question is, couldn't that antiparticle play the role of the right-handed neutrino, allowing me to write down a mass term without having to introduce extra degrees of freedom? And the answer is yes, in principle it can. So once again, mass terms couple left-handed fields to right-handed ones. So that motivates the question, can the right-handed antiparticle of nu left play the role of nu right? And here, from this, you can already see why this can only work for neutrinos, not for any other particles in the standard model, because the right-handed particle of an electron, for instance, is a positron that carries opposite electric charge. So if I were to couple, for instance, a positron and an electron in such a way, then I would have a term that violates electric charge conservation, that violates the unbroken U1 electromagnetic. So that doesn't work. For neutrinos, however, they don't carry any of the conserved charges of the standard model, and therefore this could in principle work. So let's work this out in a bit more detail and a bit more formally. What we need in order to formalize this idea is the charge conjugation operation. So charge conjugation is an operator which I'm going to call C here with a hat on top to indicate that it's an operator. And that's an operator that maps a field psi to a field which we call psi superscript little c for charge conjugate, that is defined as minus I sigma 2 sigma 0 times psi bar transpose. So that looks like looks complicated. We are going to motivate in a moment why this is the correct thing to do. Now, in order to shorten the notation, this thing up front here is something we will often call just the matrix C. And an alternative way of writing this, which also comes in handy, is you can write this as simply minus I gamma 2 times psi star. Star meaning a complex conjugate. So what I've basically, the gamma 0 that is implied by the bar here can be cancelled against the gamma 0 up front. So one important property of this operation is its effect on the chirality of a field. So if I have a field psi and I multiply this by gamma 5, so gamma 5 is the chirality operator. If psi is a positive or negative chirality state, then gamma 5 times psi will multiply psi by the appropriate eigenvalue. So let's now look at what gamma 5 does to the charge conjugate field, psi charge conjugate. So we plug in the expression from up here, and we use the fact that gamma 5 anti-commutes with the gamma 2. So this is plus I gamma 2 gamma 5 psi star. Gamma 5 in the chiral basis does not contain any complex numbers, so I can immediately pull it into the charge conjugate. So I can put parentheses here around this. And then what I have is simply minus gamma 5 psi charge conjugate. So that means that the charge conjugation operation flips the chirality. So it turns a left-handed field into a right-handed field. That's exactly what we need for our mass term. And you can also see that it, for charged particles, it will also change the charge of the particle, because this star here implies complex conjugation. So the particle creation operator is replaced by a particle annihilation operator, and the antiparticle annihilation operator is replaced by a particle creation operator. Okay, so this charge conjugation operation is a formal way of getting a right-handed field from a left-handed field. So the idea is now that we define our right-handed neutrinos to be the charge conjugates of our left-handed neutrinos. And with that, I can in principle write down a mass term. We are going to do that in a moment, but before we do so, I would like to once again make the connection between the two-component spinor notation and the four-component spinor notation, because we are often some of us are more used to the four-component spinor notation. So let me make that connection. So in four-component notation, my left-handed neutrino nu left can be written as a four-component spinor that has some two-component spinor in the upper components and a 0 in the lower components. Nu left charge conjugate is then, well, minus I gamma 2, so minus I. Then let's write out the gamma 2 matrix explicitly, which yields 0, sigma 2, minus sigma 2, 0, times the charge conjugate of psi, so chi star 0. Then applying that matrix, we end up with, let's see this now, let's put it in the next row. Because the matrix here is block off diagonal, it flips the upper and lower components, and it multiplies chi star by I times sigma 2. So we end up with a spinor that has 0 in the upper components and I sigma 2 chi star in the lower components. So a spinor that has only non-zero entries in the lower two components, that's a right-handed spinor, so that all fits together. And now what we can define is we can define a four-component spinor nu as the one that contains nu left in the upper components and I sigma 2 chi star in the lower components. So that's now a four-component spinor, but with only 2 degrees of freedom, because chi contains only 2 degrees of freedom, and the bottom two components here are not independent of the upper two components now. So this is a four-component spinor field. Representing 2 degrees of freedom. So that's, for instance, the convention that's used in the books by Weinberg, who always works with 4-component notation, even when using Majorana spinos. Right, and so this is called a Majorana spinor. Okay, now coming back to the neutrinos, let's turn this into a neutrino mass term. So we can write down a new type of neutrino mass term. In the following way. We have again a sum over flavors alpha and beta. I need a factor of 1/2 for proper normalization, which one can effectively see by deriving the propagator from this mass term. And then in order for the mass to have the correct physical interpretation as the pole of the propagator, that factor of 1/2 needs to be there. Right, and now instead of nu left and nu right, we have nu left alpha charge conjugate bar times nu left beta plus the Hermitian conjugate. Right, so it's again a mass term that couples a left chiral and a right chiral state, but the two are now related through charge conjugation. Now, that still leaves some questions unanswered. First of all, yes, it's a new type of mass term. It's in a sense a bit more economic than a Dirac mass term because it can be written down with only 2 degrees of freedom. But it still does not address the problem of why the neutrino masses are so much smaller than the masses of the other particles. And in fact, it introduces another problem. Namely, while this is consistent with all the unbroken symmetries of the standard model at low energy, it's not clear how this can be obtained from an SU2 invariant theory. So questions are, how is this obtained from an SU2 invariant UV completion? And why are the M alpha beta so small? Right, the problem with the small M alpha beta we had before. The problem with the SU2 invariant theory, that simply means if I write down this term for the neutrinos, and I remember that in an SU2 invariant theory the neutrinos are in the same doublets as the electrons, or the charged leptons, then in principle I would need to write down such terms also for the charged leptons. And that would introduce terms that violate the gauge symmetries of the standard model. So that's something I can't do. So therefore we need to talk about how to resolve this. And perhaps the most popular way to solve both of these problems is the so-called seesaw mechanism, which we are going to talk about next. So that's, let's see, my numbering is, yes, this should be 1.3. So the starting point for the seesaw mechanism is, well, there is no free lunch, so we have to give up on one thing, and the thing we want to give up on is being so economic. So we are, in fact, going to introduce right-handed neutrinos after all. So we are going to introduce these extra degrees of freedom. But we're introducing them in a different way than for the Dirac mass term. So we augment the standard model with 3 right-handed neutrino fields, which we are now in this context going to call NR. And they are supposed to be singlets under all the standard model gauge symmetries, as were in fact the right-handed neutrinos that appeared in the Dirac mass term. So they are singlets under the standard model gauge group. In order to shorten the notation, I'm now going to outline the mechanism for just one flavor of left-handed neutrinos and one flavor of right-handed neutrinos, but reintroducing the flavor indices is extremely straightforward afterwards. So for just one left-handed and one right-handed neutrino, for simplicity, with this particle content and the symmetries of the standard model, I can write down the following Lagrangian. And by Lagrangian here, I mean I'm going to write down just the terms that are relevant for the particle masses. So I do, of course, now have a Dirac mass term again, simply because it's not forbidden. So nu bar left and right. And now for these right-handed neutrinos, because they are total singlets under the standard model gauge group, for them, I can write down a Majorana mass term without having to worry about anything like embeddings into a UV completion that respects certain symmetries. So minus 1/2, let's call this MM, NR charge conjugate bar times NR plus Hermitian conjugate. So this here is again a Dirac mass term. Which again arises from the Higgs mechanism. So that means it's arising from something like a term minus a Yukawa coupling times L bar H twiddle NR as before. And this over here, that's the Majorana mass term for the right-handed neutrinos. Now, because I have these two different mass terms, the states that appear here, what I call nu left and n right here, those are not yet the physical states, because I now have two contributions to the mass matrix of the theory, and in order to determine the physical states, I need to diagonalize this matrix. So in order to do this, let's introduce the notation little n to mean an object that has two components, the upper one being the nu left field and the bottom one being n right charge conjugate. So that does not imply that this is a multiplet under any kind of symmetry. I'm just putting these two spinors, which by the way are both left-handed spinors, into this common structure. And the reason I'm going to do this is because with this I can now write my Lagrangian in matrix form. So my Lagrangian now reads minus 1/2 n charge conjugate bar times capital M times little n plus Hermitian conjugate, where this matrix M, it looks as follows. So let's see, we have minus 1/2 n bar charge conjugate. That is now a vector that has, in its first two components, it has new left charge conjugate bar. In the bottom two components, well, the charge conjugation on the NR is being undone by the second charge conjugation from here. So in the second two components, it just has NR bar. The matrix here has the structure 0, MD, MD, MM. And on the right, it gets multiplied by new left and new right charge conjugate. You can easily multiply this out to see that by expanding it, we recover the Lagrangian in the form over there. But the reason I like to write it this way is because now I have all the masses appearing here in that matrix. And it's now immediately clear what I need to do to get to the physical states. I need to apply some sort of rotation to my vector n that diagonalizes this matrix. And in order to do this, in the simplest way possible, let's talk about the orders of magnitude of the entries of this matrix. I mean, it's of course simple. It's of course simple to do this in full generality for arbitrary values of MD and MM. But what we're mostly interested in is the following situation. So let's say the natural, even though the concept of naturalness is a very slippery slope, I'm still going to use it here. So the natural value for MD, for the Dirac mass term, can be seen from the fact that this term has to come from a Higgs mechanism. And we have examples of terms like this in the standard model, namely the mass terms of the other fermions in the standard model. So based on this, we can guesstimate that a natural value for the Yukawa coupling is somewhere between the electron Yukawa and the top Yukawa. And because theoretical physicists like to set all dimensionless numbers to 1, let's assume that the natural scale here is that of the top Yukawa, which puts MD at roughly the electroweak scale. So natural values for MD are around the electroweak scale, meaning around 100 GeV. Once again, that argument is on very shaky grounds, but one can start from there and then see how things change if we relax this relatively strong hypothesis. For the Majorana mass term, we have essentially no theoretical guidance because it's not related to any of the things we already know in the standard model. So for MM, if there's something we don't know, we blame UV physics for it. So we say the natural scale for the Majorana masses are much larger than the electroweak scale. Once again, that's not a particularly strong argument. It's very hand-wavy, but the advantage is it works. Okay. Now what this means is we have a hierarchy here in the entries of our matrix with the off-diagonal elements being much smaller than the element here on the diagonal. And that means that the diagonalization of this matrix M can in principle be done perturbatively, with the result being that the eigen vectors, so the eigenstates, are a state nu left prime, which is basically identical to nu left plus corrections of order MD over MM times nu right charge conjugate. So our physical nu left state is essentially identical to the new left state we had introduced here based on symmetries, plus small corrections, plus a small admixture of this other left-handed state, the antiparticle of the NR, but with a coefficient of order md over mm, and that can easily be made so tiny that we're never going to see this in an experiment. Similarly, the NR prime is essentially the NR plus a small admixture of the new left charge conjugate. But what's more important than the eigenvectors are the eigenvalues. The eigenvalue corresponding to nu L prime is of order, it's minus m, no, it's not of order, it's exactly minus md square over mm. And the second eigenvalue is of order mm. So that means these NR prime states, they are super heavy. They live far above the electroweak scale, so they are safe from phenomenology. But the new left prime, they now have a mass that is suppressed by an extra factor of md over mm. And this is the explanation in this scenario for why neutrino masses are so small. Now there's one little caveat here still, there's a minus sign here and we don't like negative masses. However, that minus sign can be reabsorbed into a phase redefinition of the nu L prime state. So we rephase nu L prime to I times nu L prime to absorb the negative sign. In the mass eigenvalue. And this means that our low energy Lagrangian so low energy means with the NR fields integrated out. So the low energy Lagrangian now contains a term minus 1/2 md square over mm times nu left prime charge conjugate bar times nu left prime. So we've generated a Majorana mass term for the left-handed fields. We've done so by starting from a theory that was SU2 invariant, so we've solved that problem, and we have automatically obtained a coefficient here that is naturally small, whatever naturally in this context means. Now, the typical numbers that we need to be phenomenologically viable. So, to make this left-handed neutrino mass, which we call md square over mm, phenomenologically successful, we need, for instance, MD of order 100 GeV, and then based on the fact that neutrino masses are known to be of order 0.1 electron volt, we need a Majorana mass of order 10 to the 14 GeV. But of course, these types of values, they may be a guideline, but they are definitely not set in stone. You can do the seesaw mechanism, for instance, by setting MD on the order of the electron mass, and then that would put MM somewhere around the TV scale, for instance. Okay. So what we've done here effectively, I mean, I've basically diagonalized a matrix, but it's interesting to look at this also in the language of effective field theories. So what we've effectively done is we've integrated out those right-handed neutrinos, we've introduced the right-handed neutrinos, we've set their mass to a very large value, and then we've integrated them out. So in a sense, what we've done is we've started with something like this. We have a left-handed neutrino that we've coupled to the right-handed neutrino. These couplings proceed through the Higgs, in particular through its VEV. And the right-handed neutrino has a Majorana mass term, which means it's a term that flips particles and antiparticles. And so if we integrate it out, then we contract this propagator to a simple factor of 1 over mm, leading us to this Majorana mass term with the structure nu left charge conjugate, and the two insertions of the Higgs VEV that are contained in the MD squared up here. Right? So each of these here, each of these vertices gives an MD, and the mass insertion of the NR gives an MM. Now if we integrate out the MR, then that vertex here, it still contains the MD square, and it contains over 1 over MM from integrating out the propagator of the right-handed neutrino. And there's our neutrino mass term. Now I should say that this is not the only way of generating a Majorana neutrino mass term. An alternative possibility is, for instance, to couple the left-handed SU2 doublets to a triplet scalar field. So alternative ways of generating Majorana neutrino masses. Right, so one possibility is to introduce a triplet scalar delta. Which leads to a Lagrangian that contains a term of the form M times L bar charge conjugate times the triplet scalar times L. And then that triplet scalar needs to get a VEV, and then you need to explain why that delta has a smallish VEV to, sorry, this should not be an M, that should be a cover coupling. So that can be done in an SU2 invariant way. But now you have the problem that your neutrino masses now arise from the VEV of this triplet delta. The first alarm bell that might ring when I talk about a VEV of a triplet scalar is, what about the oblique parameters? What about the rho parameter in particular, which rules out large VEVs of triplets? That is not a problem here, because what we're interested in is a small VEV, because we want to explain a small neutrino mass. But the problem then is, well, we need to think about why the VEV of this particle, of this scalar, is so small. So we've kind of shifted the problem from the fermion sector to the scalar sector, but it's still a problem. Another possibility is, so instead of integrating out a singlet fermion here, you could do the same with a triplet fermion and integrate it out. So there's a number of variations of the seesaw mechanism. So introduce and integrate out. Heavy fields other than NR. So for instance, a triplet fermion. And you will find these in the literature. So what I've discussed here is what we usually call the type 1 seesaw. And you'll find in the literature, you will find names like the type 2 seesaw, the type 3 seesaw. The problem is that everyone seems to mean something slightly different by these terms. So it can very easily get very confusing. But all of them are based on introducing something and then integrating it out. Okay. So that's what I wanted to say about the theory of neutrino masses. I would now like to talk a little bit about how we go about determining neutrino masses. And I want to talk about, in particular, kinematic approaches to neutrino masses and about neutrinoless double beta decay. That means I'm leaving out the elephant in the room, which is cosmological measurements of the neutrino mass, which is in fact the most sensitive way of looking for them. But that's a topic for Yvonne. But do you have questions up to this point before we switch gears to something slightly more phenomenological?
Could you explain how this is more, because we had a question of how we cannot get a Majorana mass from an SU2 invariant theory. How is this more
how is this better?
Helpful in that scenario?
So the question is, how is this any better than what I have already erased now in getting a Majorana mass term from an SU2 invariant theory? Now the point here is that I've started from this Lagrangian over here. So this is SU2 invariant, right? And then I've integrated out the NR fields, and that has yielded this term here. But now I've basically shown that I can get this from an SU2 invariant theory by explicitly writing down the SU2 invariant theory. That's the idea here. Sure. Thanks for the question. Okay, then let's switch gears to measuring neutrino masses. So 1.4, measuring neutrino masses. So as I said, the most sensitive way of measuring neutrino masses is cosmology, which is going to be part of Yvonne Wong's lecture. And in fact, cosmology has gotten really, really close to measuring neutrino masses. So I would expect that in the next 5 to 10 years or so, we will have an answer from cosmology for how large the neutrino masses actually are. Another way is oscillations. That's going to be the topic of tomorrow's lecture. But the problem with oscillations is, as we will see tomorrow, it is not sensitive to the absolute scale of neutrino masses, but only to the differences of neutrino mass squares. So only sensitive 2 mass squared differences. Now, the first method of measuring the absolute scale of neutrino masses without invoking cosmology, so doing it in the laboratory, is a beta decay kinematics. And that's essentially the way in which we've measured the masses of most other particles from kinematics in their interactions. So an example is the beta decay of tritium. So consider the beta decay of tritium to helium-3 plus an electron plus an electron neutrino. Now the first problem here is that the electron neutrino does not really have a well-defined mass, right? The electron neutrino is a flavor eigenstate, and in the flavor basis, in which I had written down my Lagrangian at the very beginning of this lecture, the mass matrix was off-diagonal. So we first have to, in principle, have to worry about what exactly we mean by the neutrino mass here. I'm not going to worry about this just yet, for the simple reason that the experiments that use this method, they are not sensitive yet to the at the level where they'd be able to be sensitive to such details. Let me quickly see what I am going to write down and what I'm not going to write down. Right. So the basic idea here is the neutrino obviously is very hard to detect, so we'd rather go for the electron. So the idea is to measure as precisely as possible the spectrum of these electrons from tritium decay. So measure with great precision the E- spectrum from tritium decay. So graphically, that spectrum, it looks like a typical beta decay spectrum. So that's dNe over dEe. And here is the energy of the electron. And the important point here is it has a sharp cutoff somewhere, namely at the Q value of the decay. So there's a certain amount of energy available in this decay, namely the mass difference between helium-3 and tritium. And that's the maximum energy that the electron can get, right? This energy that's available in the nuclear decay is somehow split between the electron and the neutrino. And the end point of the electron spectrum is for those kinematic configurations where all of that energy goes to the electron and none of it goes to the neutrino. So, but now let's zoom into this endpoint region here. So we have here somehow we have the steeply falling beta decay spectrum ending up at the endpoint. And as I said, the configuration right at the endpoint is a configuration where all the available energy goes to the electron and none goes to the neutrino. However, neutrinos have mass. So a little bit of energy always has to go to the neutrino, namely just enough energy to create the neutrino mass. And that means if neutrinos are massive, then the beta decay spectrum will not look like this, but it will instead look something like this. With this difference down here, that being the neutrino mass. So it's clear what needs to be done. One needs to measure as precisely as possible the spectrum of these electrons close to the endpoint here, and then see if it goes down as a straight line all the way to the Q value, or see if it cuts off slightly before the Q value. The problem is the Q value here is about 18.6 keV, and the neutrino masses are of order 0.1 electron volt. So you really need to measure extremely precisely. You need a measurement with a relative accuracy of 10 to the minus 5. And an additional complication is that, of course, only very few decays even access this kinematic region so close to the end point. So you need a huge amount of tritium, and you need to reject all those decays where the electron gets only a smaller fraction of the available energy. And that's the experimental challenge. And I'm going to have a few slides towards the end about what experiments like this look like. Now, a totally different approach is neutrinoless double beta decay. So what's neutrinoless double beta decay? If you think about normal beta decays, and we consider a set of isotopes, all with the same nuclear mass number, but with different Z. So basically same total number of nucleons, but different distribution between protons and neutrons. And you plot the masses of these nuclei, then what you typically find them to be is you find them to be aligned on two curves that maybe look like some parabolas. And they alternate between those two curves. So maybe there's, let me see, I think I've now drawn this in a bad way. There's maybe one up here, then the next one is down there, the next one is there, then there's one over here, and one over there. The reason there's these two curves is that nuclei always like to have even numbers of protons and neutrons. So for instance, the upper curve here could be for the odd-odd nuclei and the bottom one for the even nuclei. So yeah, this curve here would be even. So even number of protons, even number of neutrons, and this here would be the odd-odd, meaning odd number of protons, odd number of neutrons. And this is because nucleons always like to pair together with a second nucleon of the same type but opposite spin. And if you allow them to do this, then the energy will be lower. If you have unpaired nucleons in the nucleus, then the total energy and therefore the total mass of the ground state will be somewhat higher. And of course, as you increase Z in steps of 1, you then alternate between those two curves. And now what's happening is, if you start with a nucleus that has, say, either far too many protons or far too few protons, it will want to decay. It will want to decay to a lower mass state. So you have decays that proceed this way, maybe this way, and maybe this way. And okay, this one can't decay any further then. Right, so far so good. These here over here, this is the regime of beta minus decays, and over here we have beta plus decays. But now let's consider this diagram again, and let's draw the curves a little bit differently. So let's assume we are now looking at a different but still constant A. And we draw those two parabolas let's see. So let's assume I have, for instance, I have a nucleus up here. No, let's assume I have one here, then I have one there, and then I have one over here. So now I'm in a situation where this step here, this is forbidden because it would push me up in mass. So now because of this pairing energy, increasing the number of protons for this nucleus is actually a disadvantage if it is only by 1 unit. However, what is possible is to immediately increase the number of protons by 2 units. So this one here, this is possible. So if we skip this intermediate nucleus and go immediately from that one to that one, that is now energetically allowed. And that's what's called double beta decay, because it's basically 2 beta decays happening at the same time. So this is a decay where a nucleus AZ goes immediately to a nucleus with the same A, but Z plus 2, plus 2 electrons, plus 2 electron antineutrinos. And because you basically need 2 weak interactions to happen simultaneously, that's an extremely rare process. But if the nucleus has no other choice, then it will still eventually happen. Okay, so that's some of the nuclear physics. This is called double beta decay. But there are still 2 neutrinos, so this is not yet neutrino-less double beta decay. That's just ordinary double beta decay. So in order to go from there to neutrino masses, let's look at the Feynman diagram. So we have, say, we have a neutron up here that converts into a proton, and we have a neutron down there, which also converts into a proton via a W, emitting an electron and an electron antineutrino. And the same down here. The neutron emits a W, which goes to an electron antineutrino and an electron. So that's just the diagram representing this decay. And of course, what I've not shown here is that these nucleons keep exchanging pions all the time, and that's what binds them together. Okay. Now, if you remember your first lecture on QFT, you've heard at some point that in a Feynman diagram, you can replace an outgoing antiparticle with an incoming particle. So what I can do is, if I had a source of electron neutrinos, I could, in principle, instead of having this in the final state, I could put an electron neutrino in the initial state. And now it turns out I do have a source of electron neutrinos if neutrinos are Majorana particles. Because the second part of the diagram here, that's emitting an electron antineutrino. But if neutrinos are Majorana particles, a neutrino and an antineutrino are the same particle. So I can connect those 2 lines and draw the following diagram. I have again my 2 neutrons converting into protons as before. I emit my 2 electrons as before, but now the 2 neutrino lines are joined. And all I need for this to work is I need 1 Majorana mass term in here, because I need a helicity flip. And now I have a diagram that is essentially mediating the same nuclear process, but without any neutrino in the external state. And that's why it's called neutrinoless double beta decay. And as you can see, I have this Majorana mass insertion here, which means that the amplitude for this process is going to be proportional to the neutrino masses. And that's why this process is sensitive to neutrino masses. See how much detail we want to go on this. Okay. So if you write down the rate for this process, then very rough, very hand-wavy, very dimensional analysis like, this process is going to be suppressed by 4 powers of the Fermi constant, 2 for each beta decay. So it's proportional to GF Fermi to the 4th. That already means it's going to be a very small number. Then there is obviously going to be a nuclear matrix element square, so M0 nu 2 beta square. And to get the dimensions right, there needs to be a certain number of powers of the neutrino mass and of the electron momentum. So we have one neutrino mass insertion here. The diagram gets squared. So there is an m nu squared here. And then we put in the right number of powers of the electron mass, which I think, so if the nuclear matrix element is defined to be dimensionless, then I need 3 powers of the electron mass if I did my dimensional analysis correctly. Right, so that one here, that's easy because, well, the electrons here, they're even monoenergetic, right? It's a heavy object decaying to 2 electrons, so the nuclear recoil energy is negligible. So all the energy goes to the 2 electrons, and for momentum conservation reasons, it needs to be distributed equally among the 2 electrons. And that's in fact the experimental signature, 2 back-to-back electrons with a fixed energy. The complicated part is this nuclear matrix element. Now you might say, okay, then why don't we look at 2 neutrino double beta decay, which still has a much larger rate than, it has a tiny rate, but still much larger than neutrino-less double beta decay, but it doesn't involve a neutrino mass insertion. But the problem is that the nuclear physics of the 2 neutrino double beta decay is different, because here, in a sense, the two neutrons that decay can be located anywhere in the nucleus. Whereas over here, because they need to exchange a neutrino, there's a preference for them being close to each other. And that means the nuclear physics here and there is different, and that means the only chance of estimating these matrix elements is to use first principle methods. And first principles methods in nuclear physics are extremely complicated and yield results that are fraught with large uncertainties. And that's one of the main theoretical problems that come with neutrinos double beta decay. So the nuclear matrix element for 0 nu 2 beta decay cannot be easily inferred from those measured in 2 neutrino double beta decay. And the reason is that the exchange of the neutrino implies different spatial correlations between the 2 decaying nucleons. Implies different spatial correlations between the decaying nucleons. And so they need to be inferred from first principles methods. Need to be calculated from first principles. Now, I won't have time to go into the details of these methods. There's a number of methods on the market that have different advantages and disadvantages and typically give different results. So that's a major source of uncertainty. One possibility is, for instance, to construct a nuclear shell model. Another possibility is to work with the so-called quasi-particle random phase approximation. There's methods where you effectively you try to parameterize the wave functions of your nucleons in terms of a certain set of basis wave functions, and then you hypothesize some interaction structure. You write down some interaction Lagrangian between the particles, and with this ansatz of basis states, you then try to minimize the energy of the Hamiltonian in order to determine what the ground state is. But in order to get reliable results there, you need a lot of basis states. You need complicated interaction terms, so it quickly becomes a very difficult numerical problem. So this is really one of the main challenges for Neutrinos double beta decay on the theory side. And then on the experimental side, of course, the main challenge is that you're looking for an extremely rare process, which means that you need to suppress backgrounds to a really absurd level. Okay, so in the last few minutes, I would like to quickly switch on the projector to show you some slides on the experiments that actually do these measurements. Okay, it seems that the projector has forgotten where my computer is. Let's try this again. No source found.
Before.
Yeah, of course, we tried it before. So my computer seems to recognize that something is happening because it's switching resolutions. Well, if not, then let's skip this for today. Then I'm instead going to just draw the main picture on the blackboard, and I can still show you the slides tomorrow. Okay, so since the picture I'm going to draw is about kinematic measurements of neutrino masses, I'm going to erase this slide here. So for this method, there is one experiment running not far from here, the so-called Katrin experiment, which stands for the Karlsruhe tritium neutrino experiment. And the basic idea in this experiment is, well, first of all, what you need is you need a large amount of tritium. And you need this tritium to decay, and you need to get the electrons out without perturbing them. So tritium is a highly radioactive material, so you normally want to safely store it in a sealed container. But you can't do this here because then the electrons would be perturbed by the walls of the container. So what you need is in fact what they call a windowless gaseous tritium source. So that's basically, it's a pipe that does not have any window on either side, but it just has an intricate set of vacuum pumps, which do what they call differential pumping, which means you inject tritium at one end and you pump it out again on the other end. And you do that in such a way that none of the tritium escapes you, but that still you don't need any seal, no window. So the electrons that come out can freely leave the decay region. So here we have these tritium atoms, and then the electrons move over this way. Afterwards, there is two spectrometers, a pre-spectrometer and a main spectrometer. So these are essentially, let's imagine them as some vessels, one much smaller than the other. Pre-spectrometer and main spectrometer. And in these volumes, you have a complicated and very precisely determined configuration of electric fields that first makes sure that all the electrons which are entering this system under slightly different angles, that they are all put onto well-defined trajectories, and then they are retarded in the sense that you apply an electric field opposite to their direction of motion to slow them down. And you choose this field in such a way that only the electrons that live very close here to the endpoint, so only the electrons with the highest energies, are able to pass the electric field. And you do this in two steps. First, to filter out the majority of the electrons, and then a more fine selection on those that remain. And then what you basically have is, you have it in the very end, obviously, there is some sort of detector that registers the electrons that make it through. And so for a fixed setting of this electromagnetic field, you count the number of electrons that you get above a certain threshold. And then you vary this threshold, so you vary your electric field and you repeat the measurement, and that way you can step-by-step map out the endpoint of the spectrum and determine how many electrons pass each of your thresholds, and then you can ideally determine if this curve is straight or bends over. Now, the difficulties with this approach is, first of all, of course, you need a very large amount of tritium, and then in order to get this to the precision at which you need it, these things need to be gigantic. So this is many meters in diameter, this vessel, and there's general agreement that this cannot be scaled any further. So this technology has basically reached its limitations, but it has not yet reached the neutrino masses. So the ultimate sensitivity of Katrin will be somewhere on the order of 0.3 electron volts for the neutrino mass, whereas we know the neutrino mass is to be at most 0.1 electron volt. So that experiment will most likely not see a signal, or if it sees a signal, then it will be even more interesting, because then it will be in contradiction with cosmology. So that has then far more interesting implications still. A newer approach that has been developed more recently, but is not at the level yet where it can do anything more than, say, technology demonstration, is called Project 8. I don't know why it's called Project 8. Somehow no one seems to know. No one seems to know what Projects 1, 2, 3, 4, 5, and 7 were. But Project 8 has at least survived to the point where everyone knows the name. And they've done some successful technology demonstrations, but it's not a full-fledged experiment yet. So the idea here is, you start with tritium, but then you have these tritium atoms pass through a magnetic field. So you have here your magnetic field lines. And when an electron comes in, it spirals around those magnetic field lines, right? And as it spirals around the magnetic field lines, it emits synchrotron radiation. And so when I was an undergraduate student, I once worked for a company that makes electronics for cars. So I was working on these keyless access systems that you now have in some cars. And since that time, I'm convinced that anything having to do with high-frequency technology is absolute black magic. And because in black magic you can do everything, you can actually register this synchrotron radiation. You can filter out the radiation from the electrons close to the endpoint, and you can measure it extremely precisely. And because the frequency of the synchrotron radiation is related to the momentum of the electron, you can thereby measure the momentum of the electron. And the hope is that that technology will scale better than these spectrometers, so that that will ultimately be able to reach the point where we can actually see the neutrino masses realized in the standard model. The difficulty is, of course, again, you need a huge amount of tritium. And if you just inject all of that tritium into your magnetic field, you get the synchrotron radiation from all these tritium atoms at the same time. And then you need very sophisticated electronics to filter out those that you're actually interested in. Of course, you can, to some extent, compensate this with some pre-filters. Another difficulty is to reach the precision that Project 8 aims to achieve, you can no longer work with molecular tritium. So as you know, hydrogen likes to combine into 2-atom molecules, but the problem is that the bound state of this molecule introduces theoretical uncertainties which would limit the precision of your measurement. So in order to do this successfully, you need to do this with atomic tritium. That means you first need to produce atomic tritium, and that's actually something where our experimental colleagues here in Mainz are heavily involved in building this atomic tritium source for Project 8. But then you also have the difficulty, you need to prevent it from recombining, because red chemistry tells you tritium wants to be in 2 atomic molecules. So that means it can't be too dense. You need to keep your tritium so dilute that the different atoms don't get a chance to combine. And that means that the volume that you need to magnetize is very large, and magnetizing large volumes is very expensive. But still, this seems to be a technology that might eventually be able to get us there in the laboratory. Okay, with that, I'd like to stop for today. I'd like to thank you for your attention, and then we continue tomorrow with neutrino oscillations.